Have you ever really stopped to think about the device you're watching this on right now? I mean, at its core, it's just a bunch of simple on and off switches. So, how does it handle everything from, epic video games to super complex math? Well, today, we're going to pull back that curtain and decode the incredibly clever language computers use to count.
All right, let's just jump right in with a little puzzle. How on earth can a machine that only gets two things, on and off, possibly understand a number like 2021? I mean, it sounds kind of impossible, right? But the solution is honestly so elegant.
So, our whole journey starts with this one basic challenge. Deep down, every single digital circuit, every processor is really just a massive collection of microscopic switches. And, well, a switch can only do two things.
And it really is that simple. Just picture a regular light switch in your room. It's either on or it's off. There's no dimmer, no in between. And in the world of computers, we just give those two states a number. We say on is a 1 and off is a 0. And that's it. That is literally the entire vocabulary a computer has to work with. Just ones and zeros.
Okay, so to really get how computers solve this two-state problem, it actually helps to take a quick look at the system that we use every single day, probably without even thinking about it. Right. So we use what's called the decimal or base 10 system. And it's called base 10 for a pretty obvious reason. It uses 10 different symbols, 0 all the way up to 9. But the real magic isn't the symbols themselves. It's all about where we put them.
Let's just take our number, 2021. The 1 on the far right, that's in the ones place. The 2 next to it is in the tens place. The 0 is holding the hundreds place, and that first 2 all the way on the left, well, that's the thousands place. See? Each position is just a power of 10. That's how we get 2021. Simple enough.
So, if our system is built on powers of 10, how does a computer build numbers when it only has two symbols to work with? Well, it just uses a different base. So, let's dive into binary.
The binary system is base 2. It only uses those two symbols we talked about, our old friends 0 and 1. And each one of these little digits has a special name. It's called a bit, which, fun fact, is just short for binary digit. This is the absolute smallest piece of data you can have, that single on or off state.
And here it is side by side. This is the core difference. On the left, you've got our world, with 10 whole symbols to play with. On the right, you've got the computer's world, with just 2. But here's the cool part. By using that exact same idea of positional value, just with powers of 2 instead of powers of 10, computers can represent any number you can think of.
Let's actually see how this works. Okay, so 0 is 0 and 1 is 1. So far, so good. But to get to the number 2, we've run out of symbols. So, just like we do when we go from 9 to 10, we add a new column and write 10. In binary, that doesn't mean 10. It means 1, 2, and 0 ones. Then 3 is 11. That's 1, 2, and 1, 1. The pattern is exactly the same as our own system, just with fewer building blocks.
So, what about our number from the start, 2021? Well, in the computer's language, it becomes this very long string, 111111000101. Now, to a computer, this is perfectly logical. But for us humans, that is a total mouthful. And wow, is it easy to mess up.
And this brings us to the next big problem. You've got programmers and engineers who actually need to read and write these super long binary numbers. And as you just saw, that is not exactly practical. They needed a better way, a more human-friendly shorthand.
Exactly. Can you even imagine trying to read that out loud over the phone? Or trying to find a typo in a string of 50 ones and zeros? No way. It would be an absolute nightmare. There just had to be a more compact way for us humans to deal with the computer's native language. And that better way is called hexadecimal, or just hex for short. Now, this is a base 16 system, so to get 16 symbols, it uses our normal digits, 0 through 9, and then it just borrows the first 6 letters of the alphabet, A, B, C, D, E, and F. A little weird, but stick with me. Okay, now here is where the magic happens. The whole reason hex is so incredibly useful is because a single hex digit can perfectly represent a group of exactly 4 binary digits. So for instance, the number 15, which is 1111 in binary, is just the letter F in hex. This is the secret to cleaning up those crazy long strings. And the best part is, the conversion is unbelievably simple. You just take your long binary number, and starting from the right, you break it up into little chunks of 4. If the group on the far left doesn't have 4 digits, no problem. You just add some zeros in front. Then you just swap each 4-bit chunk for its single hex character. That's it. And there it is, the big aha moment. Our messy, super long binary string for 2021, once we group it and convert it, becomes the clean, simple, and way more memorable 7E5. Now, that is a number you can actually say in a meeting without losing your breath.
So, okay, we've gone from simple switches to binary and then to hex. But why does any of this really matter? Why did we build our entire digital universe on top of this foundation?
Well, it all boils down to one word, really: reliability. It is so much easier for a physical circuit to reliably tell the difference between 2 states, like a high voltage and a low voltage, than it is to detect 10 different precise levels. This incredibly simple, super robust on-off system is the literal bedrock of all modern digital logic, and it powers everything from the very first clunky computers to this sleek 64-bit smartphone sitting in your pocket right now.
So when you think about it, every digital photo you've ever taken, every song you've streamed, every text you've sent, at the most basic level, it's all just an unbelievably long and complex sequence of ones and zeros. It's a ridiculously simple language that has somehow allowed us to build this immensely complex world. And that leaves us with one last thought. What amazing things are we going to build with these simple ones and zeros next?